Okay, hi guys. So in this lecture, we'll be starting off with seeing division and Germer experiment. So let's get started. So we'll be seeing division and Germer experiment. Okay, so this actually confirmed the wave particle or rather wave nature of moving electrons. Okay, so this confirmed wave nature of moving electrons. Okay, so what he did or they did was they have a split here or rather a slit here, and this is the path of the electron. Okay, so this is nothing but electron beam from source. We are passing through a slit between two slits, between the opening of two slits rather. Okay, and then we are placing a shield over here. So what happens from this shield is we get, after passing through this shield, the electron actually generates many radiations. Okay, and those radiations were collected on a screen. Okay, and they form concentric circles. Let me draw the full circle as well. Okay, so this experiment actually confirms the wave nature of moving electron. Okay, so this is nothing but a diffraction pattern. Okay, from a small hole on which the electron beams are bombarded onto a slit. Okay, so this diffraction pattern is actually also a wave pattern itself. So with the help of a diffraction pattern, we actually confirms the wave nature of moving electrons. So this pattern is similar to the X-ray pattern, which confirms the wave nature of electrons. This pattern which we saw the concentric circles, this is screen for capturing radiations. This pattern is similar to X-rays. Okay, or rather X-rays pattern, which confirms wave nature of electron. So let's next see an important principle, which is Heisenburg uncertainty principle. Okay, so which states that it is impossible to determine simultaneously the exact position and exact velocity of electrons. It states that it is impossible to determine simultaneously the exact position and exact velocity of electron at the same time. Okay, so we are just using the deterministic value that delta x into delta p should be more than equals to h upon 4 pi. So this is very experimentally determined, and we will not go into the derivation of it as it is out of the scope of our JEE syllabus, but you can just remember it. Okay, with the help of few questions and practice on it, you will be able to quickly memorize it. Okay, so delta x is nothing but uncertainty in position, and delta p as always is uncertainty in momentum. Okay, so we can write delta p as again m delta v. Okay, so delta x into delta v would be greater than equals to 4 upon rather h upon 4 pi m. Okay, so here delta v can be used to refer as uncertainty in velocity. Okay, so next let's extend this Heisenburg uncertainty principle for lambda as well. Okay, so for lambda we will be calculating as something we have initially that lambda equals to h upon p. So from here p can be written as h upon lambda. Okay, so dp by d lambda can be written as minus h upon lambda square, just differentiating this with respect to lambda. Okay, so from this the mod of dp upon d lambda can be written as h upon lambda square. So now we have that we can actually use the equation of we know that delta x into delta p is h upon 4 pi. From here you can write delta p equals to h upon lambda square delta lambda. So just substitute the value of delta lambda here, delta p here rather, so it should be h upon lambda square delta lambda equals to other it's greater than equals to h upon 4 lambda. So we know from now here that delta x into delta lambda would be greater than equals to lambda square upon 4 pi. So this is the Heisenburg uncertainty principle in position and wavelength. Okay, so next let's calculate for kinetic energy as well, the relationship between position and uncertainty between position and kinetic energy. So we know that kinetic energy can be written as half mv square. Let's do dE upon dV, which would be equal to mv. Now we already know that delta x into delta v would be greater than equals to h upon 4 pi m. Okay, so from here we can actually deduce that delta v upon delta e would be equals to 1 upon mv. Okay, so delta v can be put here as delta e upon mv should be equal to h greater than equals to 4 pi h upon 4 pi m. So just cancelling m and m on both the sides, and we'll be getting delta x into delta e should be greater than hv upon mv, where 4 pi, which is where v is velocity of the moving electron upon 4 pi. Okay, so with this we come to the end of this lecture. In the next lecture we'll be taking on some questions on the same to have a more practice. Okay, so till then, good luck and goodbye.